Welcome to this self-recorded presentation of branch privilege injection, a recent paper by Professor Kaveh Razavi, Dr. Johannes Wikner, and myself, Sandro Rüegge. Let me first give you an executive summary of what we did here. So back in 2018, we learned about Spectre, or more specifically about Spectre v2, branch target injection, which is arguably the most dangerous variant because it allows an attacker to control flow across privilege levels, from user space to supervisor, for example. Intel recognized this issue and introduced EIBRS, Enhanced Indirect Branch Restricted Speculation, and it is supposed to prevent this V2 by introducing a barrier between the privileges. Now Intel said, well, we fixed it, you don't have to worry about it anymore. And this was true for quite a long time. So for several years, nobody found an inherent issue in this security property of EIBRS. However, then in 2024, we found some issue, reported it to Intel, and finally, after 9 months, we were able to publish it in 2025. So what are we talking about here? This concerns branch predictors. And let me first introduce the terms we use to describe the branch prediction unit. So there's this special unit in the processor, and depending on where you are currently in the program, it tries to predict where you will go next. Now there's different components involved in this. We call it the BTB. That's a static predictor. It doesn't use history. It just uses where you are right now in the program. And then there's the IBP, the indirect branch predictor. And this one additionally uses some history information to predict where the program likely will go next. So what is the issue with this thing? So the issue is that if you execute a branch and let's say to some evil target, then the branch predictor will learn about this. And if you then execute it to some harmless target later on, the processor will think, oh, I know where this branch should go. And it will first try to execute this evil thing that you executed earlier on before it learns or before it realizes that this prediction was wrong. It will undo the changes and execute the harmless target. But at this point, it might have already left a trace in the microarchitecture that an attacker can exploit. And when this becomes dangerous is when you do this across privilege levels. So the first part, which we call training, happens in, let's say, user mode, and the second part happens in supervisor mode. There's some additional complexity involved here. For example, these two branches are in different address spaces, well, in the same address space, but at different address locations. So you will have to find what we call aliasing. Because what happens in this branch predictor is there's some hashing that determines where in the predictor it will look for a target. And if our user mode branch and our supervisor mode branch collide in this predictor and use the same entry, we can still mistrain a branch even though it has a different address. And the second place we have to be a bit careful is this evil gadget. So this evil gadget is also located at different addresses in user mode and in supervisor mode. So what we do is we exploit the fact that the branch predictor only stores partial addresses, in this case on Intel at least. In this case, the lowest 32 bits. And what we can do is we can have an evil alias in user mode. So something evil that is located at the same lower 32 bits. Okay, so this is how you can exploit the branch predictor. This was known already back in 2018. So what did Intel do to prevent this? Intel introduced what we think is a kind of a tag in the BTB. So they are able to associate a prediction with a privilege level. And in this case, it would be associated with user mode, and it would not be used in supervisor mode, preventing this type of attack. Now, we are researchers, so we didn't just believe this. Instead, we tried this. And what we observed is that we couldn't see any mispredictions in supervisor mode anymore, just like expected from this defense. However, we did not just try one experiment, we tried a lot of them. And we realized that somehow if there's a system call right after the training we do in user mode, there seemed to be a signal again in supervisor mode. A very weak one, but we seem to see a signal. So how would that happen? Let's learn a bit about how branch prediction updates work in the processor. So what happens if you execute, let's say, a certain chain of instructions? Let's look at the timeline of these instructions and what happens in the processor. So if a new branch is executed, one that the CPU has never seen before, it's located at a random address, it jumps to a random address, then there's no way it can predict it correctly. So there's a misprediction, and the CPU realizes this, resolves the target of the branch, trying to find out where it goes, and then it updates the branch prediction structures. Now, if we execute the exact same branch very quickly after the first one, this update might not have completed. And indeed, we are actually able to observe this. Now, this theory would also imply that if we delay this second branch by long enough, it will be predicted correctly, because now the update arrived in the branch predictor. And we can measure this. So here's a plot for Intel Raptor Cove where we plot the prediction accuracy, so whether the second branch was predicted correctly, against the delay in NOP instructions. And we can clearly see that the predictions become correct once the second branch is far enough away from the first one, which clearly indicates that there's some delay in updates to the branch predictor structures in Intel processors. And the way we imagine this works inside the processors, and we of course don't see Intel's RTL, they don't give it to us, so this is just a model based on our experiments, and our experiments confirm this model. So what we usually show in these slides is this direct arrow from a branch to the branch predictor. Poof, there's an entry in the branch predictor, and it's now just there. However, that's not what happens in reality. In reality, we think the processor has to work for this. We display this with a kind of assembly line, not assembly as in assembly code, but assembly like in a factory. So the processor sees this branch and it inserts it into this assembly line. It first has to collect information about it. Maybe there's also other predictions inside this queue that get inserted first. So it takes some time until all the information is available. The entry can be created in the predictor, and that's when it actually gets inserted. And this will explain the delay we see. Okay, so I've just shown you this weird delay of branch prediction updates, but what does this have to do with Intel's defense against EIBRS? So you remember this very suspicious system call that I showed you earlier on that somehow makes the experiment work again. What we can do is we can do the same delay approach here that we did earlier on. So we execute this experiment and we vary this delay, and then we execute it in supervisor mode, and we try to see whether the branch in supervisor mode mispredicts to this evil gadget. And we can plot this again. So we plot this, it's again for Intel Raptor Cove. We plot how successfully this misprediction happens, and we again show the delay in NOP instructions. And what we can clearly see is that our attack works if this system call is really close to the training. However, if we get further away, at some point, our attack stops working. And we can also plot the opposite. We can test for whether a prediction is available in user mode. It works exactly the same way, and we can plot it again, and we can see that it's the exact opposite result, which is interesting because this means two things. The first one is what we are observing here is a race condition. And this race condition between the training of the branch predictor and the system call that we are showing here, this race determines in which privilege mode the prediction will land when it goes to the predictor. And the second thing we can see here is that even though EIBRS just says it protects supervisor mode, it actually isolates both modes from each other symmetrically. So how does this fit into the model that I showed you earlier on of the processor? We think what might be happening here is that this prediction, while it is being assembled, somehow forgets to track the current privilege level. And when it finally reaches the end of the assembly line, the processor has already switched due to the system call, switched to the new privilege, and when the prediction is inserted, it actually takes the current privilege level instead of the one of the branch where it originates from. Other explanations for this might be that the privilege level is tracked correctly in the assembly line and there's simply a switch of wires in the processor when it gets inserted into the BTB. As I said, we don't have the RTL, but our experiments confirm that this might be what is happening. So what does an attacker do with this? An attacker will train in user mode and then in supervisor mode attacks this branch, which will mispredict to an evil gadget. This is very simply displayed. We show more details in the paper, but what this gadget should do then is it should go to memory, load some secret data, and then, depending on the secret data, access another piece of memory. And depending on what piece of memory is accessed, an attacker can infer the secret that was originally loaded. So what do we have to do for this? We have to find a branch in supervisor mode that we can attack, because we cannot attack just any branch easily, because we would like to control some registers to control what secret is loaded. We also have to find this evil gadget that actually leaks the memories, leaks the secret through the memory. And then again, we have to search for them during runtime, because the Linux kernel uses KSLR, which randomizes the locations of code and other components in memory. So we have to find them where they are located when the actual system is running. The other thing we have to find is the fizmap, the direct map of the kernel, the secret, and the reload buffer, because they're also not deterministically located in memory. Where did we find this issue? We looked at a lot of different Intel processors. In fact, we looked at processors back until 2012, and we found that all of these processors show this interesting delayed branch predictor update behavior. We also looked at the initial attack that we showed to you just right now during this presentation, where we kind of jumped the barrier on the syscall and due to the race condition land in the wrong predictor mode. And we found this issue on all Intel processors since the introduction of EIBRS. Then we looked at the same thing, but from virtual machine, from the virtual machine point of view, where a virtual machine attacks a hypervisor. And we found this issue on all Intel performance cores since the introduction of EIBRS. And lastly, we looked at IBPB. IBPB is a branch predictor flushing mechanism in Intel processors that allows you to separate components, security domains that are not natively separated by the predictor, for example, different virtual machines. And this IBPB is also vulnerable to this issue, at least on all Intel performance cores since the introduction of EIBRS, but also on older cores even before Spectre was publicized. So, in conclusion, we have found asynchronous branch predictor updates, which were never reported before. We have also found race conditions in branch predictor updates on Intel processors, which breaks their Intel EIBRS mitigation. And lastly, we have proposed and evaluated mitigations because we think 9 months of waiting for a microcode update is too much. So we believe that there needs to be a software solution to these issues too. What did this lead to? The disclosure with Intel took 9 months for the whole embargo, and they finally patched it with microcode updates because this kind of race condition issue is very difficult to fix purely in software. Here's a summary of our results. Thank you very much for listening. If you want to have additional details, you can go to our website, and we have published all our artifacts on GitHub.